Learning objectives. In this chapter, the users would learn the following aspects of bare PCB handling and testing. Etching process, PCB design on board etched, checking for proper etching of design on board, removing the extra residue left, water cooling to 25 degrees C, trim to clean out extruded epoxy, punch drill holes for alignment, make circuit on PCB, lithography, drill through holes for component leads. Etching and introduction. Etching is a method of making prints from a metal plate, usually copper, into which the design has been incised by acid. The copper plate is first coated with an acid-resistant substance called the etching ground, through which the design is drawn with a sharp tool. The ground is usually a compound of beeswax, bitumen, and resin. The plate is then exposed to nitric acid or Dutch mordant, which eats away those areas of the plate unprotected by the ground, thus forming a pattern of recessed lines. These lines hold the ink, and when the plate is applied to moist paper, the design transfers to the paper, making a finished print. PCB etching process. PCB etching is a process of placing the blank board with its resist image in a solution which is capable of dissolving copper. There is a need to wait until all of the copper dissolves that is not protected by the resist. Later, the board is washed for drilling and use. In this process, a strong acid is used to cut into the unprotected parts of a metal surface to create a design. In this, a metal like copper, zinc or steel plate is covered with a waxy ground which is resistant to acid. Here the user scratches off the ground with a pointed needle. The plate is then dipped in a bath of acid. This acid bites into the metal and it dissolves part of the metal where it is exposed. During this process, it leaves lines deeply or thinly sunk into the plate. After this, the other part of the plate is cleaned and then applied with thin layer of inking all over. After inking, the surface is wiped and it just leaves only the ink in the etched regions or lines. Now the etched plate is placed under a high-pressure printing press together with a sheet of soft paper. In this situation, the paper picks up the ink from the etched lines and thereby it makes a print. The etching process covers all the functions from using acid to needling, inking, and placing soft paper. This process can be repeated if one wants to create multiple copies of the same design. PCB etching process steps. Laminate the plate with blank copper foil. Apply the etching resist pattern. Remove etching material, which is generally the unprotected copper. Remove resist by leaving the copper track and pads. Drill holes. PCB design etched on board. In this modern age, it is quite common to find all electronic equipment on one or more printed circuit or PC boards with this kind of designs. In this, each board supports the smaller components. Not only this, it also supplies a wiring which links them all together. As a result, it makes assembly and construction much easier and reliable. All of the components are mounted after the etching is surrounded and protected by a thin sheet of insulating material. Further, the PC board has thin copper connection pads and tracks or traces attached to one or both sides. In case of complex multi-layer boards, there are a number of even thinner boards which are placed together under treatment of heat and pressure. The layers are insulated from one another. The starting place for most PC boards is a sheet of epoxy fiberglass which is laminated with thin copper foil. It covers either one side or both sides. One side covering is single-sided laminate and both side covering is called double-sided laminate. Checking for proper etching. There is a need to take precautions during etching. It is necessary to develop a desired pattern of pads and tracks in the etching process. Some of the important precautionary points are: it is required to remove the unwanted metal by using a computer-controlled milling or routing machine. It is necessary to remove just a narrow strip or outline trench around each wanted pad and track, not all the unwanted copper, to insulate them from each other. It is advised to leave the rest of the copper foil as it does not interfere with circuit operation. These days, a computer can create most PC board patterns by using the PC board CAD file to drive the router directly. One of the disadvantages of this computer-controlled milling routing machine is its high cost for commercial production. Due to cost factor, most PC boards are designed by using a chemical etching process to remove the unwanted copper. It involves the application of a masking pattern of etch-resistant material, which is also called resist, to the surface of the copper foils. After this, the board is placed into an etching bath, which chemically removes all of the unprotected copper foil. High-density interconnection, HDI. HDI PCB is defined as a PCB with a higher wiring density per unit area than conventional PCB. They have finer lines and spaces, smaller wires and capture pads, and higher connection pad density than employed in conventional PCB technology. High-density interconnect HDI is being used more often to meet the growing needs for more complex designs in smaller form factors. Beyond some of the most obvious electrical effects of using smaller wires, there is also an impact to the power integrity of a board using HDI. This includes different effects of mounted inductances, of decoupling capacitors, changes in plane performance due to reduction in perforation from chip pinouts, and the inherent plane capacitance changes from using dielectrics of various thicknesses. PCB board test methods. Although the main bare board testing technology is electrical, it is important to consider that non-electrical methods are also important in the acceptance or rejection of bare printed wiring boards. There are two non-electrical acceptance-rejection methods, both based on inspection processes: visual inspection and automatic optical inspection. Visual inspection. Visual inspection is a manual approach in that it makes use of people, good lighting, and some type of training defining what is acceptable and what is not, and good operator judgment. Usually a comparison to a known good product or the artwork is made. If the operator has seen the board often, he or she becomes more skilled at finding faults and looking for faults in likely locations. As product complexity has increased, we find that many modern products are not suited to this method. Many inner layer defects are completely undetectable, and even the external layer complexity is visually overwhelming. Visual inspection often remains appropriate for detecting cosmetic defects such as poor solder masking or physical damage. Such defects generally fall outside the realm of electrical testing, as they are not detected by electrical means. Automatic optical testing. There are computer-based visual inspection methods referred to as automatic optical inspection, AOI. AOI equipment compares the board or its inner layers to expected data and/or design rules that have been programmed into the controlling computer. These can be generally accepted parameters or design rule-based parameters or windows of acceptable dimensions for each specific feature on the board. As with manual visual inspection, faults found with this method can imply that there may be an impact on the board's functionality, but the board's functionality and interconnect are not directly tested. Board test using equipment. There are two types of tests used in board testing. They are universal grid system test and flying probe or moving probe test system. Universal grid test system. The universal grid test system represents a rectangular array of equally spaced test points. Generally, this is chosen to be large enough to cover the test area of the largest product type to be tested. It is common to speak of the density of test points presented. With modern grid designs, the test system grid size can be upgraded in the field by addition of electronic modules. With older designs that use wire between the grid and the electronics, upgrades may be less practical. Flying probe or moving probe test system. Moving probe, flying probe, and XY prober are all names for test systems that make use of two or more test points that can be accurately positioned anywhere on the board surface by means of a computer-controlled motion system. Probe tips can be retracted in a Z-axis direction away from the board surface, then moved in the X and Y directions to a new board location and extended again to make contact. Two probe tips are contacting the board. Dual-side systems generally provide a minimum of two independently moving probes per side for a minimum total of 4 heads. Advantages of flying probe. The major advantage of these systems is elimination of text fixtures, making these systems ideal for small to moderate volume production. Advanced flying probe systems provide highly accurate probe placement and contact the board with minimal force, leaving no discernible witness marks on most surfaces. They are very well suited to testing the finest pad sizes. Although not subject to limitations due to test point density, these systems do slow down as additional test points are added. Lithography. It is a process of printing from a flat surface. It is done by treating the PC board in such a way that the ink gets repelled except the place where it is needed for printing. By using this method of printing, oil and water do not mix. Also, text or artwork on the surface of paper or other suitable material can be printed. In the olden days, tones were used to mask the light for printing on the base material. But in modern lithography, the image is made of a polymer coating, and it is very useful in the design and development of printed circuit boards. It uses simple chemical processes to create the desirable image by exposure to light as per steps shown. The printed circuit board industry makes use of the lithography process for mass production of PCBs. Each and every step is closely monitored and controlled in order to minimize errors and maximize the desired outcome as per design. Verification and repair. The test system identifies faults on the board. Assuming that repaired boards are acceptable to the end user and that it makes economic sense to repair boards, a repair process normally follows testing. Because fixture problems, contamination problems, product registration problems, and other issues often result in false error reports, a verification process usually is added between testing and repair. During verification, a technician reads the fault data and makes confirming measurements to determine whether the reported faults are genuine. Automatic verification may be accomplished by a flying probe type system. The flying probe performs a similar analysis but does the retesting itself and displays a final result. Video camera systems may provide image capture of suspected fault sites, storing the image for subsequent recall at the repair station. Advanced systems may even suggest the repairability of particular fault sites according to user-defined rules. HDI bare board special testing method. Printed circuit technology is now being applied to high-density interconnection HDI applications that require consideration of new testing techniques. Notable examples include many types of advanced integrated circuit packaging introduced in recent years, such as area array devices, ball grid arrays, BGAs, laminate chip carriers, LCCs, and circuit boards employing direct chip attach, DCA, or chip scale passages, CSPs. When HDI parts are tested in a panelized form, the very small target sizes combined with potential expansion-contraction issues in the panel construction to place a maximum demand upon the test point positional accuracy within the fixture. The ability of the latest camera-equipped flying probe systems to locate these targets individually and probe them without marking combination with the fixture offers cost savings and makes this method of test very attractive, especially as new techniques improve throughput. Resist. Resist is a type of polymer-based thin lacquer-like layer. It is applied on the copper traces of a printed circuit board, PCBs. It is used for protecting against oxidation of components. Further, it prevents the formation of solder bridges between two or more solder pads, which get formed during the etching process. By using this layer, the electronic components not only get a professional look, but it also provides safety from possible electric short circuits. It can be used for both manual and automatic soldering process. But in this age of electronic boom, mass production is the emerging need of the hour. So resist plays a key role in designing and developing large-scale production of PCBs. It may be of different colors, but generally green color resist is used in the PCB formation. Resist comes in a variety of media that depends upon the application. The cheaper form of resist can be seen in epoxy liquid, which is silk screened through a pattern on printed circuit board. Types of resist. There are various types of resist used in making boards using the etching process. These are suitable for both mass production and single prototype boards. Some of the common etching approaches are resist ink pens, silk screening, photoresist, toner transfer. Types of resist. Description. Resist ink pens. It is the simplest and cheapest way to apply resist by applying it manually in the form of a liquid ink which dries quickly. It is done by using a special felt tip pen. It can be used for prototype production in small quantities. Silk screening. This is one of the most commonly used ways to apply a resist pattern to PC boards for mass production. In this, the desired board pattern is produced on a sheet of fine silk or nylon fabric stretched tightly on a frame. The frame is then placed over each clean blank PC board laminate and liquid resist ink applied to the copper foil from the top of the screen using a brush. It is very cost-effective for developing large quantities of boards, but not for small quantities because the silk screen masks are expensive. Photoresist. In this method, photopolymers or light-sensitive plastic materials are used for applying resist patterns to PC boards. In this, the most common photoresist material is Riston. It is available in dry film form. Toner transfer. It is one of the methods of applying a resist pattern to the PC board laminate, which proves even more suitable for prototyping and hobby use. It is done by using toner powders in xerographic photocopiers and laser printers containing various plastics. Fine pitch tilt pin fixtures. Many HDI structures can be tested with advanced examples of tilt pin fixtures. Those fixture plates very close to the product must be fairly thin, or the closely spaced holes will break out into one another. Such fixtures increase the demand for higher grid densities. These fixtures and pins are moderately more expensive to prepare than standard fixtures, but use similar technologies and processes. Excellent process control is important, as is excellent pin tip symmetry. When dealing with fine pitch fixtures, the problem of product and fixture registration must be considered. Even if the fixture is manufactured perfectly, the product may not align. Because the tooling features of the product are added in a process separate from the artwork production, the artwork and tooling features are usually misaligned. Bending beam fixtures. Bending beam fixtures are somewhat similar to tilt pin fixtures, except that they use extremely thin test pins manufactured from a special alloy. As in the tapered pin fixture, a significant number of thin supports are required near the product, where the pin tends to be held fairly straight to avoid conflict with other nearby pins. These pins are not held rigid, but are expected to buckle under force. This buckling displaces the pin sideways. The buckled portion may be located at some distance from the product plane, where the probes can be more widely separated. Once a pin is buckled, the force applied to move through a substantial travel is constant. This is very different from the case for a spring probe, where the force increases at a constant rate determined by the spring constant. Bending beam fixtures provide good immunity to witness mark damage. The basic technique has been in use in specialty situations for many years. At the interface side, these pins may mate to spring probes instead of contacting a rigid contact surface. In some commercial examples, the pin continues away from the product as a piece of wire routed to widely spaced contacts on the interface portion of the fixture. These in turn interface with traditional spring probes. Within the fixture, the probe wire is bonded in place at some distance from the product, defining the separation between the probes and wiring portions of its overall length. Such fixtures are quite expensive, and replacing damaged probes can be challenging. Thus, this technique is usually restricted to smaller areas and limited test point counts. Flying probe. The more precise examples of flying probe systems are very well suited to HDI testing. With on-head optical pattern recognition guiding the probe tips, they can contact extremely small targets, even in the presence of significant product registration problems. They can probe small features without making or disturbing the surface. These systems can be equipped with true Kelvin contact tips supporting effective single measurement fractional ohm testing, well suited to the sort of fractional ohm continuity test that may be desirable in efforts to detect precursor phenomena to latent defects caused by cracks or other geometry problems. The principal drawback is, of course, test speed. Used alone, these systems are ideal for prototype or small volume production applications, where fixture production would be quite expensive. Coupled plate. In a situation where most of the target product is relatively easy to fixture, but a DCA or CSP site is difficult, it may be possible to use coupled plate type testing. A variety of proprietary products are available, but the basic technique is fairly similar. The primary assumption is that each signal network arriving at the DCA or CSP site is accessible by a traditional probe at some other site on the board. These probe sites are used to perform a normal isolation test of the product. Continuity testing of most of the board is performed in the usual manner also. This method eliminates the need for superfine pitch probing at the DCA or CSP site and also avoids marking of the product at the site. However, the test does not perform a true DC test of continuity and may miss high resistance connections, which will be detected by a low threshold DC continuity measurement. Signals that loop from one DCA or CSP pin to another and go nowhere else may be untestable, as there is no outboard probe site at which to inject the test signal. Shorting plate. This method is employed in circumstances similar to the coupling plate method just described. In this case, however, the plate must be movable during the test. Generally, a pencil-sized pneumatic actuator is mounted within the test fixture to accomplish this motion. The plate employed here is a small, flat metal plate that is the size of the DCA or CSP site and covered with an electrically conductive rubber. When pressed against the product, it shorts together all of the pads at the DCA or CSP site. Continuity testing is performed in this condition by using the outboard probe sites to confirm that all of these networks are shorted together via the path to the DCA or CSP site. All of the networks are tested normally for continuity. Then the shorting plate is removed and a normal isolation test is performed. Key advantages of this method are the accomplishment of true DC measurements for both isolation and continuity, and the use of standard bare board test systems. In some applications, there is concern about any trace chemicals that may be left behind by the conductive rubber, although outright marking is minimal. Cleanliness of the product is critical, as the rubber or plate must be replaced when excessive dirt is embedded. As with the coupled plate, certain signal topologies are untestable or difficult to test. Removal of residual material after drilling. Once the drilling is finished, you can now remove the toner resist from the copper tracks. This is done so that they can adapt to the solder easily. The most common method of removing the toner resist is to rub acetone or methylethyl ketone over the board. Though this method is quite prominent, many people fear the nasty chemicals involved in it. To avoid any skin irritation with the chemicals, you must use rubber gloves before attempting the cleaning process. Also, the removal process should get done in the open air to avoid inhaling of fumes. However, some people prefer to use the old method of removing the residue. It is a method that involves removing the toner by gently rubbing with fine steel wool, which is applied with a little paste cleaner plus warm water. This method works well for small-scale production and is also environment-friendly. Water cooling. After removing the toner resist from the board, it is washed with water. It is preferable that this process takes place at 25 degrees C to have an effective cleaning. Conductive rubber fixtures. Several designs for fixture systems employing conductive rubber as a basic probe element have been offered commercially. In some cases, the rubber is a specialized material in sheet form and is conductive only in the Z-axis. This fixture is itself made from a circuit board with slightly raised pads to compress the rubber tightly against desired product sides. The fixture board connects to the grid electronics as its reverse side. Other designs have included various types of locally deposited rubber dots, usually of conductive rubber that is not sensitive to orientation. Again, a rubber probe is formed. Problems with cost, complex manufacturing, complex repair, dirt sensitivity, and suitability to very small pad areas seem to have prevented widespread adoption. Trimming. Epoxy is an adhesive material made up of plastic or other class of synthetic thermosetting polymers. It is a cured end product of epoxy resins, also known as polyepoxides, which is a class of reactive prepolymers and polymers which contain epoxide groups. Epoxy resins have strong mechanical properties of bearing high temperature and also chemical resistance. Epoxy has various applications in multiple fields, but it is mainly used for metallic coating of electronic and electrical components. Therefore, it is useful for the design and development of printed circuit boards used in the electronic and electrical products. The process of trimming is done to make the board to its correct size, taking due care to avoid cracks by spraying protective lacquer. There are a number of methods available for trimming. Drilling holes for component leads. The drilling of holes in the board for component leads or for PC terminal pins can easily be done after etching and washing. Drilling is easy at this stage as the toner still holds position over the remaining copper. While drilling the holes, you should remember that there are tiny holes already etched in the center of each pad. These holes actually act as a pilot holes for the drilling process. You should remember the basic diameter of the drill specified for both lead holes and PC terminal pins. Most common lead component holes are drilled with a 0.8 mm diameter drill. Apart from this, the larger components and PC terminal pins are drilled with a 1 mm or 1.2 mm diameter drill. If you are able to drill holes for a PC board, then you should pick the drill having 3 mm or 3.5 mm diameter. Due care is to be taken in selecting the right size drill bits. While making the metallized holes, wider drills should be used. This is done to make the drill acceptable by the metal layer, and also it should be wider than the lead. In case you face any confusion, you can confirm the concept from your PCB maker or guide. While drilling non-metallized holes, you can add 0.1 mm to the component lead diameter. This is done in order to counter the bad mechanical properties of solder, keeping in view the requirement to maintain reliability of the PCB. To drill square or rectangle leads, you can add 0.1 mm to the diagonal of the rectangle. For reliability reasons, you need to make several changes in your drilling process. While drilling big, flat square or rectangle leads, it is better to use slot or square holes and avoid round ones. Optical inspection. Optical inspection has been discussed elsewhere. It is generally applied early in the fabrication process as a yield improvement and data collection tool, not as a means of final product qualification. However, with the improvements in resolution, the type of defects that may escape undetected becomes somewhat more limited, and optical inspection is argued as a possible means of final testing. Combinational test methods. One technique that offers immediate practicality in resolving difficult testing situations for higher density product, often using existing equipment, is generally described as combinational testing or sequential testing. As the name implies, this is testing in one or more stages using a combination of test techniques. Combining techniques inevitably adds complication. The simplest example is the use of a universal grid to test the majority of a product, followed by a flying probe system to test HDI features and re-verify the failures reported by the grid. Software tools have simplified the process of combining test methods. Conclusion. In this chapter, the users have covered the following aspects of bare PCB handling and testing. Etching process, PCB design on board etched, checking for proper etching of design on board, removing the extra residue left, water cooling to 25 degrees C, trim to clean out extruded epoxy, punch drill holes for alignment, make circuit on PCB, lithography, drill through holes for component leads.